And welcome to today's webinar, Combining 4D STEM and in-situ experiments, enabling statistical quantification of microstructural evolution. Uh, Before we get started, I would like to cover a few housekeeping items in the next few slides. If you have a question, please submit it at any time during the presentation through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We'll attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we will follow up via email after the webinar. Now, I would like to introduce the speaker for today's webinar. Josh Ketcher is an associate professor of material science and engineering at Georgia Tech. He got his bachelor's and master's degrees in applied physics and mechanical engineering, respectively, from Brigham Young University, and his PhD in material science and engineering at the University of Illinois at Urbana-Champaign. His research area is in relating material degradation and failure to microstructure in extreme environments, including high strains and strain rates, high temperature, fatigue, corrosion, and irradiation. A large focus of his research is on developing and applying novel multiscale and in-situ electron microscopy techniques to directly resolve microstructure evolution and correlate it with failure initiation processes. His lab is also expanding into the area of sustainable manufacturing for production of metals and alloys. His research and teaching have been recognized by the Office of Naval Research, Department of Energy Basic Energy Science, NSF, ASM, and the Materials Society through early career and teaching awards. Now, over to Josh.
All right, thank you, Ben, for that introduction, and thank you everybody for tuning in. It's a privilege to be able to speak to you all today. As Ben mentioned, I'll be talking today about some of the work my group's been doing and some of the work I've been doing over my career in trying to better integrate high data throughput and data-rich techniques such as 4D STEM with in-situ electron microscopy tools so that we can really understand what drives the mechanical properties of materials, what drives microstructural stability and local deformation mechanisms. The work I'll be showing today, it's mainly the work of two graduate students, Yichen Yang and Sandra Singbi, that are co-advised by myself and Professor Olivier Perron, another professor here at Georgia Tech. Just a very brief outline of what I'll be talking about today. So I'll start out with a little bit of history and background on how we got to where we are now in terms of automated orientation mapping capabilities and microstructure mapping capabilities using electron microscopy. Also talk a little bit about the in-situ quantitative mechanical testing tools that we use for the TEM, and then go over a couple of case studies, a couple of application examples, looking at grain size distribution effects on strength and grain size effects on microstructure stability, looking at deposited metal and thin films. So my group in general, what we specialize a lot in is understanding how local microstructural conditions affect deformation, degradation, failure initiation, anything in that realm, in that world. And we work across length scales. So on the left here, for example, we see fatigue crack growth through a stainless steel sample. Here you see the crack growing. And using tools like EBSD and the SEM, you can map out the dislocation densities and defect state of the material and correlate that to the local microstructural conditions. Now in the TEM, traditionally, the approach we've been using is just in situ deformation to directly observe the active deformation mechanism. So here's a stainless steel sample, a twin boundary, and dislocations interacting with that twin boundary during deformation. However, as we've gone forward through the years, we've gone down through the length scales more, both in terms of what we're seeing and in terms of the microstructural features we're interested in. So for example, here again, we just see that those dislocations interacting with the twin boundary in stainless steel. This is a large grain polycrystalline material where a lot of what we're interested in It's just how these dislocations are acting with an isolated grain boundary, right? We can treat almost every feature as a feature in isolation to understand what's going on. As you move down through the length scales, however, so here we have an ultrafine grained gold thin film being deformed in situ in the TEM, we get to much more complex interactions where we still have transgranular dislocation flow, but grain boundary mediated deformation also starts to become very important. When we get down to the true nanocrystalline regime, then we're able to see very little in terms of active deformation mechanisms, right? We're not able to really see the dislocation flow, the dislocation interactions, but we do see the evolution of the grain boundary or the grain state itself. And that movement through different length scales has really motivated the development and search of different tools where we can really quantify the microstructure, right? We can no longer rely just on observing the deformation mechanisms. Now we actually have to quantify how the microstructure is evolving and relate that back to the mechanical properties and deformation mechanisms. So with that motivation in mind, we're going to have a little bit of a history lesson going back through time. And we're going to start out in the SEM because a lot of these tools really initiated in the scanning electron microscope. There are a number of reasons for that we'll go through, but automation in the SEM in terms of orientation mapping has a very long history now. Back in the mid-80s, David Dingley developed kind of quasi-semi-automated techniques to extract the orientation from an EBSD pattern. So here we see an EBSD pattern. It's just looking at silicon. In the initial approach, you'd go through and identify the zone axes, run it through a program to extract out the orientation. As he detailed in the paper, you're looking at about 20 to 30 seconds for every crystal orientation. Which meant you could go in there and you can get one pattern per grain if you knew where the grain boundaries were and start to get a sense of how orientation was distributed in a material. Now, a fun thing with these old papers is, I mean, I guess it's not that old, but mid-80s is they often put reviewer comments at the end of the paper itself. So if you look in this paper, this David Dingley paper, one of the reviewer comments was, do you envision a time when we can actually automate all this, right? Do you envision a time where you could use pattern recognition and actually automatically extract out the orientation state? The author said, we tried, it's looking promising, but we're not there yet. By the early 90s, though, this all changed. So the early 90s, you saw developments both in detector technology, this movement to more digital cameras, CCD cameras that took images of a phosphor screen. So you'd have an automated readout of your Kikuchi patterns, and then development in the algorithms used. So I think the biggest one was the development, or not the development, but the application of Huff transforms to these EBSD patterns, which allowed computers to easily recognize the location of these Kikuchi bands and automatically extract out the orientation state. That was commercialized through TechSem Laboratories, TSL, which through a number of acquisitions and conversions is now part of Gatan, and it fell under this umbrella term orientation imaging microscopy, the ability to take a picture essentially of the orientation state of the material. By the mid-90s, you had multiple commercial options available, and by late 90s, you saw really widespread adoption in both academia and industry. I think you'd especially see in the steel industry how certain companies in certain industries really saw the promise and advantage of being able to quantify the microstructure state and use that in terms of in aiding in material development. By the early 2000s, you saw more advanced techniques based on orientation mapping, things like mapping out the dislocation density. So one of the first papers there was published in 2000, just looking at dislocation density variations in relation to a grain boundary. And then in the mid 2000s, you saw the work of Angus Wilkinson, where he developed algorithms and approaches to extract out the elastic strain and then the stress from these EBSD patterns. So now you have the modern era where with EBSD, you're able to very rapidly, very easily map out orientation state, but also things like dislocation density, stress variations, and polycrystalline materials. You see now the combination of these techniques with in-situ scanning electron microscopy deformation. So here you have, just as a function of strain, how the stress state varies at a grain boundary. And then even more recently, the incorporation of these full field simulations, dynamic simulations, EBSD patterns, and their incorporation and use to map out the orientation state in the material. So through the dictionary approach or through spherical indexing. Now, if we look in the TEM, you saw that much slower development of automated orientation techniques, or automated orientation mapping, or microstructure mapping in general. So in 2006, you saw, or early 2000s, you saw some of the very early efforts by David Dingley, and around the same time, the team of Roche and others, taking two very different approaches to mapping out the orientation state in a material. So the David Dingley approach, this is very much an image-based technique, where you took a series of dark field images and used those dark field images to reconstruct a virtual diffraction pattern that you could then use to determine the orientation locally in the material. And then here we have scanning probe techniques coming online, where you'd raster the electron beam across your sample, collecting thousands of these diffraction patterns and using template matching algorithms to then determine the local orientation state in your material. But again, this is over a decade later than what we saw in terms of EBSD development. There are a number of reasons for this delayed development in the TEM community compared to the EBSD community or SEM community. One of the reasons is just the solid angle range that you're looking at. So in the TEM, you're looking really just at one zone axis, whereas in EBSD, you have multiple zone axes contained in a single diffraction pattern. Information density is very different, so you can see the richness of information in an EBSD pattern compared to a TEM diffraction pattern, where you're limited to just a handful of diffraction spots typically for mapping orientation. Detector technology is very differently. So in the SEM community, you have such a large chamber, it's easy to just put a lot of different detectors in there, which gave more flexibility to incorporate a specialized dedicated EBSD detector. Whereas in the TEM community, before the 2000s, you still saw most people relying on film development, where you're limiting the number of images you can take and the throughput of those images. TEM is also much more sensitive to local conditions and stage stability. So EBSD is fairly insensitive to small drifts in the electron beam. TEM, though, you can get very different diffraction conditions just by small variations in sample thickness, defect state, bending conditions, things like that. And finally, and this is more opinion, but culture itself, I think in the TEM community, there's been this stronger drive of really having an expert user of the TEM, right? Spending hours down there in the basement, applying your trade, learning the tips, the tricks to get really beautiful images. SEM was seen more of an easy technique. And in some ways that lowered barriers to bring in these automated techniques, where EBSD essentially, you just draw a box and press go and get a massive amount of data out. However, that changed in the TEM community, really with the advent of more advanced electron detectors. So here we have, this is a plot courtesy of NSEM that shows with their TEMs there, the data throughput, or the data rate that you can get as a function of the different cameras in the years when they came online. So you saw in the mid-90s, early 2000s, you just saw the initial stages of digital image collection. That led to a much higher throughput, but still not a super high throughput of the data collection rate. Once you switch to direct detectors, so moving away from having a scintillator and a camera taking an image of the scintillator to directly reading out the information from electron strikes, then you saw this huge increase in the data collection rate. So to the point where you're getting terabytes and terabytes of data a day. So with that detector technology advances, you also see advances in the algorithms used to analyze images in the TEM. Probably the most famous and widespread these days is 4D STEM technologies, really driven and moved forward by Colin Office. Where in this approach, you raster the electron beam, similar to what we showed previously. You raster the electron beam across your sample and collect thousands or even millions of these diffraction patterns. Once you collect these diffraction patterns, you can extract all sorts of information from them. Anything from the orientation state to structural information through virtual bright field and dark field images, through to electrical information, through tychography techniques, you have this very rich, these very rich data sets that you can now pull out and analyze. All right, so that brings us somewhat to present day capabilities. So now we have these very high throughput scanning techniques in the TEM. We're able to get terabytes of diffraction data. And the question is, what do we do with it? What do we do to really maximize the benefit from all of these data? What I'll be focusing on today is orientation mapping capabilities and incorporating that with in situ mechanical testing in the TEM. The orientation mapping that I'll be using, it's built into the STEMX software through Gatan, but it's an algorithm that I think is used by a few different groups at this point. Essentially, the approach is if you know the phase of your material, you know the crystal structure, you can use that to calculate the reciprocal space structure. Once you have the reciprocal space structure, you can then simulate these kinematic diffraction patterns. And you can do that for every possible orientation for a certain phase. Once you have this database of templates, kind of this dictionary of orientations, you can use pattern matching to determine which one best fits your experimental diffraction pattern. And in that way, determine the orientation locally in your material. So if we look at that, then what you can get out is anything like an orientation map of your material. This is a gold thin film. You can use confidence maps just to determine how confident you are in the local orientation given by the algorithm, and also similarity maps where you can look at the similarity of neighboring patterns to really quickly highlight things like grain boundaries in your material. Now you still have ongoing challenges with these diffraction patterns because of the signal to noise ratio and really because of dynamic diffraction concerns. So the simulations used typically are kinematic assumptions, meaning you're assuming only one electron scattering event per electron as it passes, or 1 or 0 electron scattering events. We know in the TEM though, especially once you get to samples that are over 10 nanometers thick, and we're typically looking at 100 nanometer thick samples, you get dynamic scattering effects that can lead to additional features inside your patterns that can kind of frustrate your orientation mapping. These dynamical scattering effects and just the signal to noise ratio that you're getting in these patterns typically has motivated the use of precession electron diffraction. So in precession electron diffraction, what you do is, let's see, so here we just have a range of diffraction patterns with different precession angles used. What we're doing here is, instead of just collecting electrons going straight through your sample, you're tilting your beam and rotating it about an axis. That smears out many of your dynamical diffraction effects, giving you a cleaner kinematic diffraction or kinematic pattern. The issue with this is that many of us don't have precession electron diffraction on our TEMs. So as George said, we don't have these capabilities. So it motivated us to see what types of techniques we could develop to be able to get reliable orientation maps without having to go to these hardware solutions. And to do that, we looked to the EBSD community, again, for inspiration. So with EBSD, again, a very similar technique, right? We're just scanning the electron beam across the sample, collecting thousands, millions of diffraction patterns and extract out the orientation state. One of the tools developed, let's see, about 10 years ago in EBSD is a tool called NPAR. It's neighbor pattern averaging and reindexing, where you'll collect your EBSD pattern. Here you see a very low signal EBSD pattern. You look at all the neighboring patterns and you average them together and re-index your new pattern. So now you can actually see your Kikuchi bands clearly. You get more reliable indexing. The problem with this approach is you're just kind of indiscriminately taking the neighboring patterns, so you can actually lose nanoscale features in your material. So here we have the original scan. You can see these two nano twins right next to each other. With NPAR, that can lead to some smearing and combining of features. To address this issue, a new technique called NLPAR, non-local pattern averaging and reindexing for EBSD was developed. In this approach, instead of just averaging neighboring patterns together, you develop a weighting factor. This weighting factor measures the similarity of nearby diffraction patterns and uses that to calculate a weighting factor. So very similar patterns will have a high weighting factor, dissimilar patterns will have a low weighting factor. So if a pattern is collected across a grain boundary, it's going to be very dissimilar to that original pattern. So it's going to have a low weighting factor, so it's not going to be averaged together. This allows you to preserve nanoscale features in your scans. Now, this has been developed, this again was developed about 5 or 10 years ago for EBSD. We've now incorporated, working with David Rowenhurst, we've incorporated into STEMX and 4D STEM analysis. There's some differences. First off, you have to blank out the direct beam. The direct beam in TEM patterns is usually much more intense than surrounding beam and can really wash out surrounding information. Also, to boost the signal, we take the square root of the intensity just so that we get more of the background information in. So if we walk through how this is done in the TEM, if we just look at one feature around this kind of triple junction point here, this map is created, right, by collecting a whole bunch of local diffraction patterns, which you see here. You can see across this boundary, the diffraction patterns look a little bit different. So when we calculate our weighting factor, so first we blank out that direct beam, so we get more of the scattered beam signal. We can then calculate the weighting factor. You can see all the patterns within a single grain have higher weighting, so they're more similar. We average those together, and we get our final kind of NL stem filtered pattern. So here's the original pattern. After NL stem filtering, you see that you can more prominently see these diffracted beams to higher scattering angles. So you essentially have more information contained in these patterns. We can look more closely just at an intensity profile in your original diffraction pattern compared to an NL PAR or NL stem process diffraction pattern. So here in the black line, you can see these high noise levels, these high local fluctuations in intensity. These are largely smoothed out from the NL PAR processing. And you start to be able to see these very faint diffraction patterns start to appear more prominently in your diffraction patterns. All right, so that's some of the theoretical background. I'm going to show just some examples of NL stem in practice. We're going to show just some examples of this NL stem in practice. I'll say for the remainder of the presentation, all the data collected, we collected using a Metro 300 camera. So this is a Gatan direct detection camera that gives you higher signal to noise ratio. It doesn't have some of the noise levels that you see in CMOS or CCD indirect detection technology. And all the orientation mapping is done with Gatan STEMX orientation mapping capabilities. So first example, we'll just look at a nanocrystalline nickel sample. So in this material, we're actually dealing with a very small grain size, about 10 nanometer average grain size, 10 to 20 nanometer. With 100 nanometer thick film, it means that we're looking at multiple through thickness grains. They're somewhat columnar, so it's not too much mixing, but that will have an effect on our results. So if we look at the as collected data set, you see we get actually pretty good indexing rates. We're indexing about 90% of the grains just with the as collected patterns. But you do see these white points. So these white points are the unindexed points. There are quite a few of them, especially at the smallest grain sizes and around grain boundaries. On the right here, we see after NL stem processing, we actually get to 99.9%. We're almost getting 100% indexing rate just through this post-processing of the diffraction patterns. If we look at the diffraction patterns themselves, we see this boost in the signal to noise ratio. We see diffraction spots appearing to higher scattering angles, but we still do have some mixing of the patterns. You see these kind of spurious points. And this is just because there are almost no grains that are entirely through thickness. So we get some mixing still. Now, if we look at a larger grain material, we see a much larger benefit of this NL stem processing. So here we have a gold thin film, an E-beam evaporated gold thin film, and we did a series of irradiation experiments on these. So here we have just as deposited state. We irradiated these materials at Sandia National Lab in collaboration with Khalif Hattar there. We irradiate them using self-ion irradiation to induce a number of irradiation defects in the material. So these typically appear as small dislocation loops. DPA is just how many displacements per atom. It's a measure of how heavily damaged we expect the material to be. We see, as expected, as we go to higher irradiation levels, we get lower and lower indexing rates. So we start out at about 90% by 5 dPa. So this is a heavily damaged microstructure now. We drop below 80% indexing rate, which is expected. We have a lot more defects in the material. It's going to affect our electron scattering and decrease kind of or increase the noise levels in our pattern. What's really interesting though is as we apply NL stem processing to these patterns, we actually see increasing indexing rates with increasing damage levels. So in the initial as deposited thin film, we get almost 100%. We're just below 98%. But by 5 dPa, we're essentially at a 100% indexing rate. So what's going on here? Well, there are two effects really. One of them is we're just increasing the signal to noise ratio, right? You average patterns together, it's going to increase the signal, decrease the noise, increasing the success that you have for these template matching algorithms. But you also have a secondary effect as well. As you irradiate the samples, you're going to add curvature locally to your microstructure, to your crystal structure. And what that gives you is essentially an inverted precession electron diffraction effect. So with precession electron diffraction, you're rotating your electron beam at a fixed angle, collecting signal from kind of a wedge in reciprocal space. Here, what we're doing is we're not rotating the electron beam, but the crystal rotates. So as we collect diffraction patterns over an area, we get this averaging over a range of crystal orientations, and we get essentially a precession electron diffraction effect. So that's why we think we're actually getting higher indexing rates as we go to a more damaged film. And this is just one film, or just one slide to say this is not limited to metallic materials. So we have a collaboration with Professor Asif Khan here at Georgia Tech looking at HCO. So this is a complex oxide material. You typically get very weak diffraction signals, especially because we're dealing with very, very thin samples, which leads to a very low indexing rate in our as collected diffraction patterns. When we apply NL stem, now we can resolve that nanocrystalline microstructure as well as the larger grains much more clearly. It's still a challenging material to work with. We're still just at 80% indexing rates, but it's a huge improvement over what you'd get just from the as collected diffraction patterns. All right, so now just a few words on the state of in-situ mechanical testing inside the TEM. So in-situ mechanical testing, in-situ deformation actually has a very long history in TEM. Almost from the earliest days of TEM, people were putting deformation stages inside the TEM to see the dynamics of how materials deformed, how things like dislocation interactions occurred. So this is just dislocation interactions in a titanium sample. Most of these experiments were done using a kind of crude but very effective approach. So this is an old Gatan straining stage. The way it works is you take your sample, you bolt down the two ends, you polish the center so you get an electron transparent region in the middle, and then you pull it. You don't know the strain state, you don't know the stress state, but you can watch dislocations interact for hours. You get this very stable platform for observing dislocation interactions. More recently, and this is already, this type of work has been going on, say almost 20 years now. You've seen the advent and incorporation of quantitative mechanical testing platforms. There are a few different flavors of this. There are things like nanopillar and nano-indentation experiments and push-to-pull experiments. What I'll be talking about today and what I'll be using for the results I'll be showing is this quantitative mechanical testing using MEMS devices. So there are a few different flavors, but essentially they all work off of this principle that you have a thermal actuator that allows you to strain or apply a controlled load onto your sample, while also reading out the stress state of your material. So you can get quantitative stress strain curves while observing the deformation behavior inside the TEM. I'm not going to go too much into detail into these MEMS devices. This is really the work of my collaborator, Professor Perron at Georgia Tech, but we have a number of publications that you can reference to see the details of how they work. Essentially, so here you have just an overview of the MEMS device. These MEMS devices integrate with a biasing holder, an in-situ TM biasing holder, that allows you to control this thermal actuator that when it heats up, it applies a load or a displacement here where your sample is mounted. We have a stationary beam that we use for reference, and depending on the movement of the MEMS device in relation to the stationary beam, we can calculate the local stress state of our material. We then use essentially a digital or virtual extensometer approach or a digital image correlation approach to calculate the local strain state of our material as well. So we can do these very quantitative, very rigorous quantitative stress strain tests inside the TEM while directly observing the deformation behavior. All right, so with that, we're going to move on to a few different case studies, a few different applications, looking at how we can combine this orientation mapping, this microstructure quantification, with in situ mechanical testing to understand how microstructure dictates the mechanical behavior, microstructural stability in our materials. The first one we'll look at is gold thin films, looking at the influence of grain size distribution on the mechanical properties and mechanical behavior of metal thin films. So here we have just two gold thin films. We have an as deposited gold thin film where we made these samples using e-beam, evaporation, and lithography to make lots of little dog bone samples. So here we have the material in its as deposited state, and here we have the material after annealing it at 350 degrees Celsius for half an hour. What you'll see is in both cases, you have these relatively larger grains. So you can see these here. What you have in the as deposited state though, is a surrounding nanocrystalline matrix. So you can see that more clearly in the orientation maps on the right, where you have this very, very strongly textured 111 texture, but you also have these nanocrystalline randomly oriented grains. When you anneal the film, unsurprisingly, the large grains grow at the expense of the small grains. So you're left with just this very strongly textured 111, fairly uniform grain size distribution material. Here we just have quantitative plots of the grain size distribution. I'll just point your attention to the small grain size regime, where we see in the as deposited state, we have a significant population of these sub 40 nanometer grains. When we anneal the thin films, we almost completely eliminate these sub 40 nanometer grains, and we're just left with more of these ultrafine grain materials. When we look at the mechanical behavior, we were actually really surprised at what we initially saw. So based off the Hall-Petch effect, you would expect as you increase the grain size, that you will decrease the yield strength of your material. These grains are relatively, they're small, but they're not in the inverse Hall-Petch regime. They're still above 10, 20 nanometers in diameter. So we don't expect inverse Hall-Petch effects to be important here. What we saw though is that if we compare the strength of the as deposited film to the strength of the annealed film, we saw this huge increase, about a 70% increase in the yield strength of the annealed thin film. We also annealed at 700 degrees Celsius. I'm not going to talk about that. At that point, your grains are so big, you get very different behavior out of it. We'll just focus here. We see we more than doubled the grain size. And with that doubling of grain size, we got a 70% increase in yield strength. This was only true at the lower strain rate. So this is 10 to the negative 4, pretty close to a quasi-static deformation state. When we went to higher strain rate, so now 10 to the negative 1 per second, so 1 per second, we see that the strengths collapse onto each other. The two lines collapse onto each other. So it's only at low strain rates, so we get this very large difference in mechanical strength of our materials. So we can see that here as we plot out the strain rate sensitivity. In the as deposited state, the strain rate sensitivity is actually very sensitive to the strain rate itself. As we increase the strain rate, the film gets less and less strain rate sensitive, as opposed to the annealed thin films where the strain rate sensitivity stays fairly constant across the strain rate regimes. All right, so what's going on? Now we can go in there and directly observe the actual active deformation mechanisms. What we see is in the as deposited state, you get very prevalent grain boundary migration happening. This grain boundary migration is almost exclusively large grains growing at the expense of surrounding nanocrystalline grains. So this is just one example, playing on loop during stress relaxation. You see this grain boundary here jump up, a fairly significant distance, 10, 20 nanometers. You also see some dislocation activity as well. Now, if we compare that to the annealed thin film, here you see very minimal grain boundary migration, but you see very active dislocation flow and interactions, almost like what you'd see in a large grain material. So you have dislocations nucleating here, propagating across the grain, piling up the grain boundary over here. So all the kind of classic transgranular dislocation mechanisms that you would expect to see. So we do see this very clear difference in deformation mechanisms in the two different films. We can combine this with the orientation mapping just to get a more quantitative and more direct view of what's happening. So here we have just TEM images before and after deformation, two different examples compared to the orientation state of the material. So this is the initial microstructure of the material. Here we have the initial grain outlined here, and the final grain is outlined here. What you see is this relatively large grain growing at the expense of the surrounding nanocrystalline material. Here's just a second example showing the same thing, where you get essentially a doubling in the grain size from before to after strain, and this grain size increase came almost exclusively at the expense of these surrounding nanocrystalline grains. We can also see, so just to recap, we see that in the as deposited film, grain boundary migration is very prevalent, and it's coming at the expense of large grains, or it's coming through large grains growing at the expense of surrounding nanocrystalline grains. In the annealed film, we don't see much grain boundary migration. We see more of the classical dislocation activity. We use a kind of digital image correlation approach to map out the strains in our films as well. Now, this digital image correlation approach, we're not actually applying any sputter pattern to our material. What we're using is immobile triple junctions in our material. So we establish criteria for saying which triple junctions are immobile and use that as our fiducial markers for mapping out plastic strain or total strain state in our material. What we saw was really interesting, or to us was really interesting at least. We saw that at low strains, the strain was very concentrated in these bands of small grains. So you get this concentration of plasticity in these chains of nanocrystalline or smaller grains in the material. As we go to larger grain or larger applied strains, the strain localization shifts to these larger grains. So now this grain is carrying most of the plasticity in the material. Here's just a second example showing a necked region after deformation. So here we show the, the blue lines show the initial grain structure and the orange lines show the final grain structure. You can see you have this large grain that's carrying a lot of the plasticity growing at the expense of these surrounding small grains. If we look at what's actually going on inside the TM, it's a little bit of a busy video, but what you see is this rapid nucleation and propagation of dislocations across this relatively large grain. The nucleation and propagation of these dislocations is happening simultaneously with grain boundary migration in the opposite direction. So what we think is happening is you have disconnection activity leading to grain boundary migration. This induces transgranular dislocation flow in your material. So just to summarize this first part, what we see is as we anneal these gold thin films and eliminate these unstable nanocrystalline grains, we see this large increase in the yield strength of our material. The reason for this is that these small grains are mechanically unstable. When we apply a load, we get rapid grain boundary migration, and this induces then plasticity in our larger grains and yielding at a lower yield stress. Grain boundary migration, though, is really only active at the slower strain rates, or at least it's very prevalent only at the slower strain rates. Once we get to the higher strain rates, we shut down this grain boundary migration, and we get very similar yield strengths for the two different materials. Now we'll go to a second example, and this example is really taking advantage of the statistical data sets you can get using 4D STEM. Now we're just looking at nanocrystalline nickel thin films, where we don't have this large grain size distribution. So we can't as easily directly observe deformation mechanisms, but we can collect very large statistics. So these data sets I'm showing now, I'm just showing a subset of the data set, and each material we analyzed over 20,000 grains to understand what was happening in terms of microstructural stability. So first I'll just show some quasi in situ results, where we took a E-beam evaporated nickel thin film, strained it in situ in the TEM, collected microstructure or collected orientation maps before straining and at intermediate stages of strain, and tracked which grains were growing and which grains were shrinking. What we saw, so here we have in the blue line the full initial grain size distribution. The grains that shrunk were all the ones in the lower end of the grain size distribution. The grains that grow are all the larger initial grains. So unsurprisingly, large grains grow, small grains shrink. But you see a little bit of a complicating effect that the large grains are almost all 111 oriented, and the small grains are almost all 101 oriented. So we're not able to differentiate between orientation effects and grain size effects. To try to differentiate between those two different effects, we took 3 different films fabricated using different approaches. So just E-beam evaporation, sputter deposited, and sputter deposited on a substrate with elevated temperature. These 3 different films had very similar initial grain sizes, but the grain size distribution was the texture of the 3 films was fairly different. So in the E-beam evaporator, we have this 101 textured thin film. In the sputter depositor, we have a 111, 112 textured film, and in the elevated temperature sputtering, you get a 001. What's interesting though is in this type A film, which is what we're calling the E-beam evaporated, the grain size distribution is insensitive to texture. Whereas in the type B and C films, we have texture sensitive grain size distributions. So in type C, we have a stronger, or the 100 grains are larger, and in type B, the 111 and 100 grains are larger. Now, if we see what happens then after we deform the materials in terms of the texture development, we see in the type A film, which the grain size was insensitive to texture, the texture doesn't really change before or after straining. The grain size changes, but the texture does not. In the sputtered film, where the 111 grains are larger, we get sharpening and strengthening of that 111 texture in the material. In the type C film, where the 001 grains are larger, we get strengthening of the 001 texture element. So essentially what we're showing here very clearly is that independent of grain orientation, larger grains always grow at the expense of smaller grains. Now we can do the exact same experiments, but now at elevated temperatures, just slightly elevated. We're going up to 100 degrees Celsius. So at 100 degrees Celsius, we don't get any grain growth without applying a load. But when we apply a load at 100 degrees Celsius, you see rapid grain growth, and we see texture evolution in all of the films. So in the type A, we start with a 101 orientation, and we move to more of a 111 orientation. Here we start with a 111, 112, and we strengthen that 111. Here we see a large increase in the strength of the 001 texture. Essentially what we're seeing across the board is that low surface energy grains, so the 111 and 001 grains, grow preferentially in the material. So what's happening here? We don't have thermally induced grain growth. We still need the stress in our material, but what we think is happening is the stress is providing energy needed to overcome kinetic barriers to grain boundary migration. So without elevating the temperature, we just get grain growth dictated by the initial grain size. Once we increase the temperature, then we get grain growth driven by the texture in the material. Basically low surface energy grains growing due to stress overcoming kinetic barriers. We'd really only be able to see these effects. You don't see these effects when you only look at a handful of grains, but by looking at tens of thousands of grains and actually running through the statistics, you're able to actually extract out and see these effects. So that brings me to the end, just to kind of summarize and recap. We're really excited in my group about the state of in situ and data-rich electron microscopy. We're excited about these possibilities now that you have. We're able to get true statistics of how your microstructure is evolving under different external stimuli. Pairing of these approaches allows you to extract out really nuanced effects of microstructure on both the mechanical properties of your material and localized microstructure stability. So with that, thank you for your time, and I'm happy to take any questions.
Yeah, thanks, Viraj, for that excellent presentation. Some really nice results there. So for any of you in the audience, feel free to submit questions. Again, just a reminder, if we don't get to your question here, we will email you an answer as well. So feel free to submit questions in the questions pane. I have a couple questions so far. One, how do you calculate the indexing success rate for your 40 STEM data sets? Some of them, there were some white regions that you said couldn't be indexed. How do you calculate that success rate?
Sure. So the indexing success rate, whenever you're conducting these orientation maps, you always have a reliability index associated with the template matching. And the reliability index is essentially a measure of how well the template matches the patterns. It's a little bit arbitrary what you call as unindexed, but we essentially just set a reliability index cutoff as we're saying this is indexed and this is not indexed. So unindexed grains, that's really just or unindexed patterns are patterns that just fall below a certain reliability index threshold. Setting that threshold is really, it's based off observations. You can usually tell when looking at these orientation maps when something just doesn't make sense, when you have noise in the patterns, and you can use that to set the reliability index threshold.
Okay, thanks. Another question that has just come in, can you calculate strain for amorphous materials?
So there are ways to calculate strain in amorphous materials. Let's see. I mean, I guess there are a few different answers to that. One, we can definitely calculate the total strain for the material, right? We can, these approaches that we're using, they're very amenable to amorphous materials. And so we can calculate the strain on the full sample. In terms of the local strain, that gets more challenging because you would need a fiducial marker, essentially. And there are a few ways you can do that. You can use roughness of the edges of your samples as a fiducial for a virtual extensometer. That would give you the average strain across the width of your sample. There are also ways in amorphous samples using 4D STEM to calculate the elastic strain locally in your material. Christoph Gammer, he's done a lot of work in that area where you can collect these diffraction patterns. And a diffraction pattern from an amorphous region, that's just going to be this kind of halo, this ring. And you can look at the aspect ratio of that ring to calculate the local elastic strain in your material. So you can get local elastic strain, you can get global plastic and elastic strain, and you can get somewhat local plastic strain. Yeah, so there are approaches and techniques for that.
Okay. Another question, a couple of people have asked about what happens when you have multiple different grains through the thickness of your material. If the grains are overlapped, what happens there?
Yeah, so that if you have too much overlap of different grains, then you're just not able anymore to reliably index the diffraction pattern. It's just a template matching technique. So if you have one diffraction pattern, or if you have one grain that's contributing most dominantly to the diffraction pattern, then the template matching is still going to be able to pick out that grain. So it's just going to give you one grain orientation based off the dominant diffracting grain. If there are multiple grains that are diffracting essentially the same amount, the algorithm's going to have a difficult time picking out one individual diffraction pattern from that set. So you're probably just going to get very low reliability indexes.
Yeah.
There are definitely opportunities for algorithm development there to deconvolve diffraction patterns, but that would take significant algorithm development.
Yeah, sure. Okay. Let's see. How do you how can you determine the accuracy of these orientation measurements? Do you have a sense for how accurate they are, or are there alternative methods to double check this?
Yeah, that's a great question. We have a number of different ways of independently validating the results we're getting. One of them is, my group has a lot of expertise in a technique called transmission Kikuchi diffraction. So it's very similar to EBSD, except instead of collecting backscattered diffraction patterns, you're collecting transmitted diffraction patterns in the SEM. What the advantage there is you can get much higher spatial resolution than traditional EBSD-based techniques. So you can get spatial resolutions on the order of about 5 nanometers. So with these thin films, we did, early on especially, we did quite a bit of EBSD and TKD and comparing that to what we were getting just from the 4D STEM-based orientation mapping. We also compared what we got from 4D STEM to precession electron diffraction results, and they all showed very consistent results. So we use a number of different, techniques to cross-validate the results that we're getting.
Okay.
We got excellent agreement in all of them, so at this point we're fairly confident going forward, just trusting the orientation mapping results.
Yeah. Okay. So that brings up another question. How far can you push the spatial resolution of the 4D STEM orientation maps?
Yeah, so that is entirely dependent on your TEM. I mean, if you think about the largest factor with 4D STEM spatial resolution is going to be your probe size.
Right.
There's going to be some broadening of your beam as you interact with the sample, but if you're dealing with a very thin sample, then you're really just going to be governed by your probe size. And at this point, you can have sub-angstrom probes, so you can actually get, angstrom resolution with 4D STEM mapping. Now, what cool. That means in terms of an orientation map, I mean, if you're looking at a single unit cell, it gets kind of complicated there, but yeah, whatever the resolution of your TEM is, you can get that resolution with 4D STEM essentially.
Okay, and then a corollary to that, how large an area can you capture in a reasonable amount of time?
Sure, so the maps that I showed for the nickel sample, those took about 5 minutes to collect, and they're faster detectors as well. So your limitation in space is probably going to be dictated more by your sample than by the actual collection. Again, each one of those maps took 5 minutes. In EBSD community, we're used to running scans for hours often. So within hours, you could, you're going to be limited much more by your sample than by scanning speeds or anything like that. So you can look at microns of material in a typical sample.
Okay. And then how long does it take to process the data? I guess two related questions. How long does it take to do the NLPAR pre-processing? And then how long does it take to do the orientation mapping?
Let's see. So it's just running on a standard desktop computer. I think that the NLPAR processing takes, for those nickel or gold scans I was showing, probably takes 5 or 10 minutes to scan. And then the orientation map, processing the orientation states takes another 5 or 10 minutes. So it's really not much of a limiting factor. We're looking at 10, 20 minutes of time to go from the raw data to your orientation maps.
Okay, nice. I probably just should pick a few more questions. There's been quite a few coming in. For the 40 STEM data sets presented here, was the camera direct detection camera, a hybrid pixel detector? Was it scintillator based?
So it's a direct detector. It's that all of them that I showed here were direct detector using a Metro 300. So there's no scintillation. It's all just direct detection. We've actually done the same. We've done the same work using scintillator-based cameras, so using something like a OneView, and you can actually still get pretty good results. It's just once you get to lighter elements, the noise levels get too high and you're not able to get reliable orientation maps anymore. So yeah, it's all with direct detection technology.
Okay, nice. Yeah, and I'll just add one more note there about the direct detection, that all of Gatan's direct detection cameras are also doing what we call counting. So they're direct detection, but they're also, you know, locating these individual electron events one by one. Last question, and then we're out of time. But for those of you we didn't get to your question, we will try to address those offline. But last question here: can you map different phases as well as just the orientation of a single phase material?
Yeah.
And
yeah,
is that something that could be done in the future, if not today?
Yeah, there's no reason why you can't do phase mapping as well. So we do quite a bit of phase mapping. All you do is when you're loading in your templates, you just load templates for 2 different phases. So each phase that you add essentially is going to double the analysis time, but that's all done offline. The reliability of phase mapping is going to be very dependent on the phases, though. You're essentially just looking at one zone axis, and there are many phases that at one zone axis look very similar to each other. So I'd say phase mapping, it's doable, it's possible, it's being done. It's not at the reliability level of EBSD yet, but it's getting there.
Okay, great. Well, thank you again, Josh, for the excellent webinar and for answering a bunch of these questions here. And yeah, this webinar will be on our website and on our YouTube channel in a few days. So thank you all for joining.
All right, thank you.